Swayamprabha. Digital India. Educated India.
Greetings. This particular video is about assignment that we are giving for week 7 and week 8. So far we have given objective type assignment, whereas in week 7 we have given programming assignment. Week 7 forms matrix solution procedure and it is necessary that you practice them. Hence, we have given a programming assignment. There are 3 languages possible: C, C++ and Python. We have given 4 problems, one based on Gauss elimination method, second problem based on TDMA procedure, and third problem based on LU decomposition, and fourth problem based on iterative procedure. Coding language is part of this course. Hence, you must know any one of these languages and start programming and become part of the CFD community. In the week 8, we discussed in detail a test case problem, that is flow in a lid driven cavity, and we have demonstrated with the help of a MATLAB code. We are also providing you the complete working code as a separate link, and to strengthen further this knowledge, we are giving you advice to practice more problem. So, this particular video is talk about what all the problem that you can try with this knowledge. You are most welcome to use this MATLAB code as it is, or you convert this MATLAB code to any language that you are comfortable with, for example C or C++ and Python. In our regular CFD course, this is how we practice. All the students are encouraged or given assignment to start coding right from the beginning itself. For example, they will start writing the diffusion equation, then they will slowly build the code as we proceed with the syllabus content. We are trying to do a similar one in this exercise also. Now, I am going to explain something more about assignment that we wanted to practice for week 8. So, problem that we have considered in the week 8 was lid driven cavity example. We defined the problem, we defined the boundary condition, we mentioned the top wall or the lid is moving from left to right with a specific velocity condition, and for velocity we used Dirichlet boundary condition, and for pressure we used Neumann boundary condition. The cavity in 2-dimensional situation is a square. If it is a 3-dimensional situation, it becomes a cube with a dimension of 1 meter by 1 meter by 1 meter, and this is the illustration we used to explain the problem as well as the boundary condition implementation. So, on the left you see explanation for velocity boundary condition. Top is the lid moving with a velocity 1 meter per second and v equal to 0, and all the 3 sides velocity equal to 0. And for pressure, on all 4 sides we have Neumann type boundary condition. So, accordingly in the x direction it is dou p by dou x equal to 0, in the y direction it is dou p by dou y is equal to 0. Now, based on this, the same problem can be extended and you can try any one of these problem. We have used central scheme for convection term. If you can recall, in week 5 we taught different other schemes, for example pure upwinding, quick scheme, hybrid scheme. Increasing the Reynolds number will have the reflection on effect of these schemes. Hence, you can try changing the code from central differential scheme to any one of these schemes and try increasing the Reynolds number to understand yourself the behavior of these schemes for different Reynolds number for the same set of mesh. In the problem demonstration, we have used top lid moving with a constant velocity, for example, u is equal to 1 meters per second. It is also possible to oscillate the lid with the sinusoidal velocity, that is a sin omega t, where a is the amplitude which is related to some major length scale related to the problem, for example, length dimension of the cavity, and omega is a frequency. You can try with a different component. So, this will give you not linearly moving lid, but it will give oscillating lid. So, instead of square, you can also try a cubic cavity. You can also try changing the aspect ratio. So, it becomes deep cavity or shallow cavity depending on the definition of aspect ratio and depending on the value of aspect ratio. So, aspect ratio means depth to the width. And we explained the problem with only primitive variable, that is u momentum equation, v momentum equation and continuity equation. You can also include any other scalar equation. For example, you can include energy equation and solve for temperature distribution. Here again there are two further possibilities for boundary condition. One, you can use constant heat flux boundary condition, other one constant temperature boundary condition. Then predict Nusselt number variation and understand the thermal characteristics associated with this flow. Another possible variation, we have explained the problem with the top lid moving. It is not necessary only the top lid should move, you can also have all other side walls also moving. It is possible that the side walls move with the same direction of the velocity, or they can move in the opposite direction of the velocity. Next problem that we advise you to try, flow through a backward facing step. We explained this problem much earlier, however, I am interested to explain that problem again. So, the inflow is on the left side. You can have a fully developed flow velocity profile explained as given here, u of y with some expression as a parabolic expression. Then on the top is a wall with the boundary condition u is equal to 0, v is equal to 0. Then you can define different step height d and get to know the effect of step height on the flow parameter. Then you have this as a wall, the side step is also a wall, and then bottom is also a wall. We understood the behavior associated with this problem. Flow separates at the beginning of the step as I am showing here, then it comes back and reattaches on the bottom wall as I am showing here. Then there is a eddy or recirculating zone. Prediction of the recirculation zone is very important, and especially in the case of you deal with temperature or energy equation, then prediction of skin friction along the wall is also important. We also know there is a corner vortex that is formed, and slowly it becomes a recirculating region depending on the Reynolds number. There is also a secondary circulation formed on the top wall as I am showing here. This again depending on the Reynolds number, hence you can try increasing the Reynolds number and observe yourself whether you are getting a secondary bubble on the top. The third problem that we can think of is flow in a conduit. So, flow through a circular cross section pipe as I am showing here. You can give at the inlet either a parabolic velocity profile as it is described here, or you can prescribe a uniform velocity at the inlet. If you are giving a uniform velocity at the inlet, it will take a long channel for the flow to develop and become a fully developed velocity profile as it is shown here. If you are giving already a parabolic profile which is very close to the fully developed condition, then you need only a smaller length and flow will develop. Again, boundary conditions are given, u is equal to v is equal to 0 on both the sides wall. So, velocity u in x direction is a function of y, and velocity is maximum at the mid plane of the free surface. Next problem we can think of is flow for a cube in a channel. It is a 3-dimensional problem. So, one view is shown here, the top view is shown here, the cube is actually placed in one view as I am showing here, and in the from the top you get to see figure as shown here. Once again you can have a variation in the inlet velocity condition, either you can prescribe a uniform velocity as I am showing here, or you can also prescribe a fully developed velocity profile as we did in the previous example. Prediction of this flow is very interesting. We also observe the flow, understand the presence of the body and separates at this point and flow go around the geometry and create different interesting fluid dynamics phenomena behind the geometry. The next one, flow in a channel with a cavity. The first problem that we discuss is a closed cavity. It is also possible to have a cavity as part of the channel, and that is what is you are seeing here. So, the top is a wall and this is a channel, and suddenly you are experiencing a cavity. It is like combination of cavity and backward facing step. So, for short cavities a weak vortex is formed and occupied downstream half of the cavity, and for long cavities boundary layer fluid is ejected into the cavity causing separation and forming a strong vortex. So, you have two such possibilities. The last problem that we are advising you to try is external flow. So far we have done internal flow. It is also interesting as well as important to know how the scheme behaves differently for external flow. External flows we are discussing two important problems, flow past circular cylinder, flow past square cylinder. The two problems are given. So, if you have the code written, then it is only a change in the geometry from circular cylinder to square cylinder. The difference is in the case of circular cylinder, separation point as marked shown as shown here is not fixed, it changes according to the Reynolds number, and that dynamic change of the separation point results in different wake pattern. Whereas, in the case of square cylinder, separation points are fixed whatever the Reynolds number, and that gives a different wake pattern. So, as far as week 8 is concerned, I repeat again, we are sharing you MATLAB code. You are most welcome, use that code as it is, or you can take that code format and write your own code in whatever language you are comfortable with, and try all this problem. There is no submission, it is only to increase your confidence level and for better practice as well as to understand behavior of different schemes. We will have separately one small assignment as in the previous weeks, a multiple choice question, but that is not that much learning unless you practice CFD with your own code. Thank you.